Today, our speaker is Dr. Herrmann, and thanks for John, Eddie, to give his name. But that was a good suggestion. So, Dr. Jeffrey Herrmann is the St. Abbo of Fleury Chair, engineer and professor in the Department of Mechanical Engineering at the Catholic University of America. He's a member of Society of Catholic Scientists, IISE, ASME, and the Design Society. Dr. Herrmann earned his bachelor degree in applied mathematics from Georgia Institute of Technology and received his PhD in industrial and system engineer from the University of Florida. Previously, he was a professor at the University of Maryland. Dr. Herrmann received the Society of Manufacturing Engineers Jere Outstanding Young Manufacturing Engineer Awards and was selected as a diplomate of the Society of Health Systems. In 2016, his textbook, Engineering Decision Making and Risk Management, won the EE Joint Publisher Book of the Year Awards. He's associate editor from the ASME Journal of Autonomous Vehicles and Systems. I hope you guys enjoy it, and all yours.
Okay, well, thank you for that introduction, and I'm very grateful for the opportunity to talk to you today. I hope that the hurricane offshore will stay offshore and not cause you any problems. And I do appreciate the invitation to give this seminar. Today, I'll be talking about our work on meta-reasoning for robots. This work involves collaborations with many other faculty and students. It's been funded by different agencies, and I certainly am grateful for all that assistance and support. And I'll mention some specifics on that as I go through. I'll give a little overview of meta-reasoning and how we can use that in developing robots and autonomous systems. And then I'll just give some highlights from a couple of projects where we've used meta-reasoning. First, I would just say that, from my perspective, robots and autonomous systems are already and going to be in the future very helpful to people, and especially in terms of doing dirty, dull, and dangerous tasks. So here we have, next slide. So here we have an example of some robots exploring a dirty subterranean area where it can be very dangerous for people to explore. Next slide. This is a photograph of a robot that's available for use in hospitals. It performs the pretty dull routine task of moving medications and supplies around a hospital. And thus the nurses don't have to do it, or their staff don't have to do it. And that gives them more time for taking care of patients, which is what they greatly enjoy. Next slide. This is a photograph from the company Skydio showing one of their unmanned aerial vehicles or drones doing a bridge inspection. Bridge inspection can be a dangerous activity. So by using a drone, the bridge inspector can stay on the shore safely and collect the data that is needed for doing this bridge inspection. Next slide. So there are all types of robots and autonomous systems, and many of them use artificial intelligence, but there are problems. This quote here, AI ML applications deal with novel situations poorly. They engage in abnormal system behavior when confronted with outliers. They struggle to adapt to changing contexts. They're ethically and legally unaware. They lack causal reasoning capabilities, and they don't possess human imagination and creativity. That quote is from Professor Modney at USC and appeared in a recent proceedings from the National Academies. So AI is great, and obviously we need more artificial intelligence, but it's not the whole solution. Next slide. And moreover, these autonomous systems have limited onboard computational resources. Here's a few of the specs of a Skydio X2 drone, similar to the one that I showed earlier. So it has a limited size. It weighs 1.325 kilograms with its battery. And because of the limited battery, it has a limited flight time. And it has certain processors. Now it has an NVIDIA system on a chip with a couple of CPUs and a GPU and lots of RAM, right? And this all seems like a lot today, but it's limited, it's finite. And the complexity of the AI algorithms that are needed for autonomy keeps increasing. And so in the future, no matter what processors we have on board our system, that's going to create a limit to the algorithms that we need for autonomy. Next slide. So as a way of studying that problem, I'm looking at meta-reasoning. So meta-reasoning is meta-reasoning about reasoning or deciding how to decide. This figure with the 3 levels is a common figure when talking about meta-reasoning. This image comes from a work by Cox and Raja in a very useful book about meta-reasoning that came out some years ago. And in this image, they divide a robot or autonomous system into 3 levels: the ground level, the object level, and the meta level. So the ground level encompasses the actual system that's moving around in the world, sensing the world, perceiving the world. And it sends information, data, to a reasoning level, or to the object level, I'm sorry, which does the reasoning. So the object level includes all of the algorithms that we're normally used to, right? The object detection algorithms, the mapping algorithms, the planning algorithms, the control algorithms, all that type of algorithmic work is reasoning. And that's generally, at the end of the day, what it does is tell the robot or autonomous system what to do next: move forward, move backward, deploy a robot arm or whatever. Okay, so that loop on the left between the ground level and the object level, that's sort of the normal thing that we think about with robots and autonomous systems. And for meta reasoning, we add a meta level. That's the 3rd level over on the right there. The meta level performs the meta reasoning. And meta reasoning is monitoring and controlling the object level. So it's reasoning about the reasoning processes. Now, to make that more concrete, let's give an example. Next slide, please. Okay, so here we have on the lower left, we have an image of an unmanned ground vehicle, a type of robot, right? This is a large robot that has lots of sensors, LiDAR, camera, IMU, GPS, a wide range of things. And it can move around the environment and take pictures and detect things, okay? Now, that's the ground level, the vehicle itself and its sensors. In the middle here, we have the object level, which is reasoning. And here I have a diagram of the Army Research Lab ground autonomy stack. I'll talk about this a little bit more in a minute, but for now, the important thing is that it has a wide variety of algorithms that do perception and mapping and planning and navigation and all that stuff. Okay, so that's reasoning, and it's controlling the robot, right? It's telling the robot what to do. Then we have meta level. And the meta level can be any kind of algorithm. Here I've shown a simple loop type of algorithm that selects which planning algorithm should be used. I'll talk more about that in one of my examples. Typically, we want meta reasoning to be fairly lightweight because we don't want to add a bunch of overhead to the reasoning level. I already said that the computational resources that are available are limited, and we don't want to add a bunch of overhead that's just going to cause more problems with our limited computational resources. So we want to keep meta reasoning relatively simple. Although in general, of course, it can be a complicated optimization problem. Next slide. So what does meta reasoning mean? Like, what does it do? Well, there are different types of meta reasoning modes, which is basically what does the meta reasoning do? And so this table is a list of some meta reasoning modes based on our work and the work of other people who've been implementing meta reasoning. So the first one listed there is algorithm selection. That is a very common meta reasoning mode. The meta reasoning policy decides which algorithm should be executed at any point in time. And so it might switch from using one type of planning algorithm to another, for instance. But that's not the only possible meta reasoning mode. There are other meta reasoning modes listed here. The meta reasoning might adjust certain parameters like search time or some parameter of a search algorithm. It might adjust different policies. It might stop an algorithm, tell it to stop running. It might directly control the interior functions of an algorithm. It might pause an algorithm and restart it. It might deal with communication between this robot and another system. And it might decide that certain algorithms need to be offloaded to other computational resources because this system just doesn't have the resources to do that algorithm anymore. There are many different things that meta reasoning can control. So that's the meta reasoning mode. Next slide. Now, where do we actually implement meta reasoning? Well, this depends, of course, upon the type of system and the type of autonomy software that the system has. And there are many, many different choices for this. These three figures indicate some of the possibilities. On the left, we might implement meta reasoning as a separate process running on the vehicle. It might even have its own computer, actually. So it's not taking up resources from anything else. So it can be completely separate where it's monitoring and controlling the autonomy software. Now in this slide, I've drawn a very simple autonomy software block diagram, just as kind of to represent the idea. But I know every system's autonomy software is much more complicated and of course varies from system to system. Now in the middle, we have a different way of implementing meta reasoning. We can implement meta reasoning as a module in the autonomy software. So whatever the autonomy software is doing, we add another module, we put it in there, we let it talk to some of the other modules, and then that can do the meta reasoning. This is particularly useful in a system if it's using ROS or some other type of structure. Finally, we might implement the meta reasoning directly in the autonomy software. So in this figure on the right, I've showed that we might implement the meta reasoning like inside the mission planning software. So it's doing meta reasoning, it's just that it's tightly integrated with the code that's doing mission planning. And this might be useful for making the meta reasoning more lightweight if all of it's doing is affecting the mission planning module. There's no real optimal solution here. Like I said before, it really depends upon the nature of the autonomy software. It depends upon the nature of what meta reasoning is doing. Is it monitoring and controlling the whole autonomy stack or just one little part of it? And again, it's an engineering choice where to implement the meta reasoning. Next slide. Okay, so suppose I want to use meta reasoning on my robot or autonomous system. How would I go about doing that? Well, after picking the meta reasoning mode and thinking about how I implement it, I really have to come up with a meta reasoning policy. So the meta reasoning policy is the rule that actually does the controlling, right? It's some kind of it might be as simple if a rule-based system. It might be a small algorithm. It might be an iterative thing, whatever it is. How do I come up with that policy? Well, that's what I call meta-reasoning synthesis. So meta-reasoning synthesis has 3 steps that lead to the meta-reasoning policy or policies. The first step is the definition. We want to define what are the relevant state variables. What variables are relevant to making, to controlling the reasoning process. Moreover, we want to identify the set of reasoning options. If meta-reasoning is going to do algorithm selection, then it needs to have a set of algorithms that are the options, right? And it picks an algorithm from that set. If it's doing some kind of parameter adjustment, then it needs to have a range of parameters or a set of parameters that it might use. Okay, so first we kind of define the meta-reasoning problem. The next step is to characterize the performance of the reasoning options in different states. Okay, so I have a bunch of different algorithms, I have a bunch of different states. I'm going to have to do some characterization. Now, I might do that in simulation, where I can control everything and I can run things really quickly and easily. But I also might have to do, experiments in the field, right, where I'm actually running these things to see how well they perform. I might be able to do some kind of analysis, but that's only going to work in certain limited cases. Fine. So by doing the characterization, I obtain data about the performance of the reasoning options. So now I know when this situation occurs, this algorithm does very well, this other algorithm does very poorly, for instance. Okay. Now I take that data about the performance of the reasoning options, and then I do synthesis. I analyze all of that, and I create meta-reasoning policies. And there are different ways of doing that. I might do that by inspection, by looking at the data, looking at data visualizations and determining what I want the policy to be. I might use some type of statistical approaches that can cluster the data in certain ways, or do some kind of regression or something like that. Or I might use some kind of machine learning approach where I'm learning a regression function or learning a classifier that would end up being my meta-reasoning policy. The key thing here is that the characterization and the synthesis are done offline, usually, before we actually operate the system. So all this is done ahead of time, okay? Remember, we want the meta-reasoning to be somewhat lightweight. So we don't want to do all this on board online, okay? Now we can do that. I mean, we've looked at some reinforcement learning techniques, but I think in general, it's best to do it ahead of time and then take that meta-reasoning policy and implement it in the system, in one of the ways in which I mentioned before. Okay, so just to recap then. So we have to determine the meta-reasoning mode. We have to determine how we're going to implement the meta-reasoning, and then we have to synthesize the meta-reasoning policy through this 3-step approach. Okay, now what I'd like to do is describe 2 different projects where we've done this, and I'll try to use this same framework to talk through those. I'm going to have to skip a lot of details, and I apologize for that. There'll be some references at the end, and of course, I'll be happy to share information with anyone who wants more details. Next slide. So this first project was part of our cooperative agreement with the Army Research Lab, the University of Maryland, College Park, the University of Maryland, Baltimore County, and other universities are all part of this partnership. And we were collaborating with some people at ARL to look at meta-reasoning in resource-constrained environments. Sydney Molnar is the graduate student who did most of the work on this, and Robbie McPherson, Matt Muller, and Lawrence Rhodes were some undergraduates who worked with us last summer to help out with some of the implementation. Next slide. So the situation we're looking at is a robot that gets stuck. So here we have an image from a simulation of an unmanned ground vehicle trying to navigate through a simulated environment that has a lot of trees, as you can see, and it's trying to get to its goal location. Now, this robot has a path planner, and the robot can detect the trees, and it knows the trees are there. But for whatever reason, the path planner has gotten the robot into this situation, and the path planner is not able to find a way out and around these trees so the robot can continue to its goal. So the robot's just kind of like sitting there, doesn't really know what to do next. It's really stuck. And this is really unfortunate, but it is true that in environments with obstacles, these autonomous systems can get stuck. The path planners just cannot find a solution. It happens. No algorithm is immune from that. Okay, next slide, please. Okay, so in this project, we were looking at the ARL ground autonomy stack. And this image provided by ARL gives you a little idea of what is in that autonomy stack. You can see the 4 different modules: the perception pipeline, SLAM, symbolic planning and execution over on the right, and metric planning and execution. So the perception pipeline takes in the information from the cameras, the LiDAR, depth sensors, other sensors. It does object detection. It can estimate poses and positions, and it feeds in information into SLAM, simultaneous localization and mapping, which is also including information from the GPS, the IMU, odometry, other information. And it creates a map, a cost map for the robot or vehicle. That then goes into the symbolic planning and execution module, which is mostly focused on mission planning. It also has some behavioral planning. Finally, that goes into metric planning and execution. And this is primarily concerned with navigation. And as you can see there on the bottom right, this module and this autonomy stack includes 2 different planners. It has a global path planner and a local path planner. So the global path planner is determining the overall route from the robot's current position to a goal location, generally through a set of waypoints. And the local planner is determining how the robot should move in order to get to the next waypoint. All of that then goes into a controller, which then sends commands to the robot. So we were doing simulation experiments with a simulated robot that was running this ground autonomy stack. And we were looking at the problem of this robot getting stuck because the planner gets stuck. Next slide, please. So here's the meta-reasoning problem. Okay, our meta-reasoning mode is going to be selecting the global and local path planners. Now, the autonomy stack is developed by ARL. It's used by many researchers, not only at ARL, but also at different academic partners. And people have come up with different global and local path planners that they've implemented in the autonomy stack. We did not write these algorithms. We did not implement these algorithms. They already existed in the autonomy stack. And that's all these acronyms you see there in the middle. And I don't have time to go into what all these mean, but there are a variety of different algorithms. Some of, well, yeah, okay. And so the state variable here is the status of the path planners. Has the path planner come up with a feasible solution, or is it iterating, or is it just basically given up and because it can't find a feasible solution to the next waypoint or to the global goal? The reasoning options are combinations, right? We need a global planner and a local planner. So these are all different combinations of global and local planners. And then the performance measures that we're looking at are the success rate. What is the likelihood that the robot will get to the goal? And how long does it take to get there? Okay, now we want to look. So in terms of implementation, I will say that we're looking at a ground autonomy stack that's built on ROS. So in terms of implementing this, we looked at different options, but we ended up basically just implementing another module in the autonomy stack, another ROS node that communicated with the existing ROS nodes that were in there. Okay, so for characterizing the different planner combinations, we did more simulation experiments. Next slide, please. So this is an overhead view of our simulated environment. You can see in the middle there a bunch of the tops of different types of buildings, some big buildings, some little buildings. You can see different roads. You can see trees in the upper left, especially. The red dashed line represents one of the routes that we were testing. The other colored lines are not meaningful here, but this just gives you an idea. We were putting the robot in the simulated environment, giving it a path, and pressing go and seeing if the path planners would get the robot to the goal. Okay, in some cases, the robot was able to get to the goal. That was great. In other cases, it couldn't. And we kept track of all that information for the different path planner combinations. Next slide, please. So based on those results, we looked at the success rates of the different combinations, and we came up with these meta-reasoning policies. We had two what we call sequential policies, which operate using a simple loop, as shown on the right there. We start with one combination. When that gets stuck, we go to the next combination, and so on and so forth. We also looked at a parallel policy that fixed the global path planner, but then it ran 3 different local path planners simultaneously in parallel, and it would switch between them as necessary. Next slide. We then took all these policies, ran them again on all the same simulation environments, and to determine if the meta-reasoning helped. And the meta-reasoning did help. It led to higher success rates, as shown here. And it did reduce the time as well. Okay, so we saw that the meta-reasoning policies were able to reduce the number of failures and increase the success rate of this robot running this autonomy stack in these simulated environments. Now we still have a lot of work to do, and we've been doing it, looking at other aspects of the meta-reasoning. Other aspects of the path planning, such as when to switch path planners, and we've been working on implementing this policy on a clear path Jackal robot. Next slide. Okay, this project was sponsored by the Air Force Research Lab. It was on planning and meta-reasoning for multi-agent systems with variable communication availability. And I was working with 3 faculty colleagues at the University of Maryland in engineering. And we had a team of graduate students from mechanical engineering, aerospace engineering, and systems engineering. Next slide. So the problem here was that we want to have a team of unmanned vehicles like drones, as shown in this picture, to do some type of search task, like to search an area for, like a search and rescue or something like that. But communication might be unreliable due to environmental factors or, in a military setting, enemy behavior. So how can these agents or drones collaborate when they can't communicate? And our approach was, and our project was to study whether or not meta-reasoning might help in this situation. And again, we looked at algorithm selection, as shown as in this little cartoon. Each of the drones has to decide which collaboration algorithm to use. And in this particular little cartoon, we can see 4 of the drones, FEAC, they can communicate successfully, as shown by the little blue bubbles. But the other 2 drones, B and D, are unable to communicate. They know that they're not receiving any signals or any information from the other drones, okay? But they still want to try to get this mission done as quickly as possible. Next slide, please. So we looked at 3 different types of missions, all in the general area of collaborative search, acquisition, and tracking. Collaborative visit, where all the targets are known ahead of time. Collaborative search and visit, where the agents have to find the targets. And then collaborative fire monitoring, where we have pop-up targets representing the spread of a wildfire through a region. Next slide, please. This little video shows the collaborative search and visit. On the left, the agents are able to communicate reliably, and you can see how they spread out and take on different parts of the search problem. On the right, the agents are not communicating, and you can see how they're all bunched up, and it's going to take a lot longer for them to search this area because they're basically repeating each other's work because they're not really communicating about who's going to do what. Next slide. Okay, now we have a multi-agent problem here. So meta reasoning requires a little bit more thought. We have to think about how we're going to do the meta reasoning in this multi-agent system. Now, there are different ways of doing this, and we did a review of the literature on that, which is cited here. But in this project, we decided on an independent meta reasoning structure. The agents are communicating and collaborating at the object level, like task assignment, but each agent does its own meta reasoning. They don't collaborate at the meta level. And the reason we did that was because we're looking at a situation where communication is unreliable. So if a vehicle is unable to communicate with others, we need the meta reasoning to still work by itself and to tell that agent's reasoning or object level to what to do, how should it proceed, even though it can't communicate with the others. So that's why we chose that structure for this particular application. Next slide, please. Now, within each agent, this figure kind of shows what's going on. We have the 3 levels. Here, the blue box at the top is the meta level. The orange box in the middle is the task object level, which is doing task planning. And the ground level is really not shown. The object level is doing task planning. So it's processing the sensor information, updating its beliefs, allocating tasks, planning tasks, executing tasks. It's communicating with the other agents, as shown by the little blue cloud at the bottom. But then we added this meta level at the top, and it's taking in the information about the communication availability, either kind of like low availability or medium or high. And then we have a meta reasoning policy that selects a collaboration algorithm based on that vehicle's estimate of the communication availability. Next slide, please. So the meta reasoning problem is to select a collaboration algorithm based on the state variable, which is the current estimate of the communication quality. We looked at a number of different algorithms. Most of these are already in the literature, and we wanted to see which ones would do best. And our performance measures were the time to complete the mission. And also we looked at the number of messages that were transmitted between the different agents. Now we took all these different reasoning options, and we did lots of different simulations and different levels of communication quality. And then we came up with a meta reasoning policy. Next slide, please. So on the far left of this figure, you'll see 3 little drones, A, B, and C. And drone A is our focus here. And it has to estimate the communication quality. So what it's doing is it's listening for what we call heartbeat messages. Each vehicle would be sending out these regular periodic messages at a fixed rate, just saying, here I am, here I am. And the other 8 other drones would be listening for these messages. Now, this was all done in simulation, and I don't have time, unfortunately, to go into the details of how we simulated that. That was a whole nother part of the another challenge in the project. But in any case, Agent A would listen for these heartbeat messages, and based on how many were actually received, it would estimate this communication quality. If it received all of the expected ones, it knew the communication quality was great. If it received only some of them, then it knew that communication quality was poor. And based on our experiments, we came up with 3 different levels of communication quality: high, medium, and low, as shown here. And we had a meta-reasoning policy that selected a collaboration algorithm based on that communication level. So if it's high, we use a genetic algorithm. If it's medium, we use decentralized Hungarian. If it's low, we use the performance impact algorithm. Okay, next slide, please. So this kind of shows how it might work. So this is just one example or instance over time. The communication availability goes from low to high to medium. The agent's perception of the communication estimate of the communication quality is shown there on the vertical axis. You notice it starts low, then it increases up to high, then it goes back down, and then it sort of converges into the middle. But as this estimate is changing, going up and down, the meta-reasoning is switching the collaboration algorithm. So in the beginning, it tells the agent to use one collaboration algorithm, then it switches to another one, and then another one, and so on, as the communication quality changes. So this is just showing how the meta-reasoning is monitoring and controlling the reasoning process. Okay, next slide, please. So we did more and more simulation experiments to test this meta-reasoning policy over a wide variety of scenarios. And so we had different levels of communication quality, as shown there on the far left. And then we had these different missions: the collaborative visit, and the collaborative search and visit, and the collaborative fire monitoring. And our results showed that using meta-reasoning did reduce the distance that the vehicles had to travel, which was our surrogate for the time to complete the mission. In some cases, it also reduced the number of messages, but in other cases there were trade-offs. So in these figures, we have the blue dot is the meta-reasoning, and then the red dot and the other dots represent the other algorithms without meta-reasoning, but just used all the time. Okay, next slide, please. Okay, so beyond these 2 projects, we've been looking at meta-reasoning in a number of other areas. As I mentioned before, we're starting to implement the meta-reasoning on a Jackal robot that's running the ground autonomy stack. We're looking at multi-agent pursuit evasion, where the agents have different pursuit strategies, and the meta-reasoning tells the agents which pursuit strategy to use based on the position of the evader. And we have some other ideas for extending that work into more complicated problems. And we've also been looking at the perimeter defense problem. In perimeter defense, we have a team of agents that are limited to a circle or other geometric shape around a target. We have intruders that are trying to get inside the perimeter, and the defenders have to move around the perimeter in order to get to the intruders before the intruders can get through. And there are different algorithms for that. So again, we have an algorithm selection problem. Which algorithm should the defenders use? Next slide, please. My ultimate goal in this research is to really look at comprehensive meta-reasoning, right? We have a finite set of computational resources. There's a bunch of reasoning algorithms that have to use those resources. We really want meta-reasoning to optimize the use of those computational resources. It's really kind of an allocation problem. How much computational resource should be allocated to which algorithm at a certain conceptual level in order so that the algorithms can come up with the best solutions in terms of controlling the robot, given the finite computational resources that are available. One idea that I've had is to model this as a Markov decision process based on the object level dynamics, not the robot dynamics. But this is still kind of definitely a exploratory idea, and still have a lot to do in terms of, formulating this and beginning to try to solve it. But that is sort of where ultimately I think this research can go. Again, with the caveat that we want to keep the meta reasoning fairly lightweight. So, maybe we have to come up with simple rules or some kind of partitioning. I don't know. There's still a lot of work to do there. Okay, next slide. Okay, so just to kind of summarize, the work that we've been doing on meta reasoning is motivated by and will advance a variety of applications. And we've been doing all this meta reasoning research and learning how these different meta reasoning policies operate, how well they perform, and really trying to move this from a pure, research activity into really an engineering activity, right? And how can we actually systematically design and develop and implement meta reasoning policies for robots and autonomous systems. And at the beginning of this presentation, I kind of indicated some of the steps in that. There's more work to do, more experience to be gained. Okay, and next slide, please. Okay, so this slide lists some of the publications we've had over the last 3 or 4 years on these meta reasoning projects that I've done, and I'll be happy to share these with anyone who's interested. So, just to wrap up, I'd like to thank you again for the opportunity to talk with you and talk about our research on meta reasoning. And I certainly welcome any ideas you have about using meta reasoning to improve the performance of robots and autonomous systems. And with that, I will conclude, and I hope I've left some time for some questions.
Is there a mic, or do I just yell?
It picks it up pretty good.
Yeah, awesome. Okay. Thank you so much for the cool talk. I love to hear about meta reasoning being used in agent architectures on autonomous systems. I had a question about your sort of process diagram where you tried to characterize the behavior of the components ahead of time to come up with these policies, these meta reasoning policies that you use. And I'm just wondering what your opinion is as autonomous systems have to confront sort of more and more dynamic situations that are further and further from what the original designers could have imagined. Does that mean that it's going to be harder and harder to characterize ahead of time the behavior of the components, and more of that meta reasoning policy synthesis is going to happen at runtime?
Yeah, that's a great question. That's slide 11 in terms of that synthesis process. And that's a good point, right? And that is something that people are always worried about in terms of writing algorithms for these systems. Yeah, so having adaptive meta reasoning would be valuable, for a system that's going to operate for a long time on its own with no ability to update it. That we would certainly have to look at that. Otherwise, we can rely on updating the control system, updating the meta reasoning policy, if we have that ability to communicate with the system, or if we can bring it back into the lab or the garage or whatever, and hangar or whatever, and update it. But that's a good point you make. Thank you.
Thank you for this talk. It's super interesting. It's a great topic. When I meta reason about my wife's driving, it never goes well. So I really like this topic. But my question was about the study that you did with the multi-agent search and the changes in policy along the way, and with differences in communication ability between the nodes. And my question was with regard to how long the nodes plan ahead, and if you thought at all or saw in the study an effect where, while there was high communication between the nodes, presumably all the nodes could gather all the information about not only the tasks that remain, but where the other nodes are.
Right.
And you could come up with a global solution during that time that would still presumably be valid if the state doesn't change, like for the remainder of the mission. But if the state does change in some way, meaning like the larger set of goals, there's like some finite period of time where like your knowledge about the world sort of decays away, and then it really would be advantageous maybe to pick a different strategy. But I was wondering if maybe you would see that effect in your study or had a chance to look at that at all in terms of the amount of, like, your ability to know everything and come up with a good plan at that point.
Yeah, I think part of that is the planning horizon. I think that's related to what you're talking about. Because if each agent knew the global plan for the whole time horizon, then each agent could just follow that. Now, one of our students did look at a situation like that, where there was no communication after an initial allocation. But after that, there was just absolutely no communication, and the agents were totally on their own. And he looked at some different policies. That was not part of this study I discussed today, however. I do not remember off the top of my head the planning horizon for what we did. Some of the algorithms did create long-term plans, and I believe that the agents would continue to follow those if they lost communication. But I don't think that was true for all of the algorithms, and I'm unfortunately I cannot remember the details past that right now. But thank you for the question. That's a very good point you make.
Can you imagine that in 50 years, when we have planning algorithms that are actually robust and collaboration algorithms that actually can tolerate communication dropouts, that we will not have need for this meta-reasoning Band-Aid on top of our systems engineering?
Oh, great question. Thanks. Well, I think the meta-reasoning problem will change because, I mean, unless systems actually have, nearly infinite computational or extremely large or extraordinarily large computing resources, like if systems were continuously connected to the cloud and had access to as many computer servers that they wanted and could instantly communicate with all of them, which might happen in 50 years, I guess. But until that happens, any autonomous system is going to have finite computational resources available to it. And meta-reasoning is about using those finite resources as effectively as possible. So I think the meta-reasoning problem will change. It will go from algorithm selection, because you're right, maybe we have the perfect algorithm already. But there's still going to be a lot of other things competing for those finite computational resources.
So that's very interesting stuff. And I was just wondering if some of your simulations are available online for us to play with them and try out meta-reasoning.
The short answer actually is no at this point in time. But it is a very important challenge to make such simulations available in the future, or for each other. And to that end, we've submitted a proposal to NSF to develop a community research infrastructure that would stand up simulation resources for multi-robot systems research and enable people to use a common set of simulation models and algorithms for autonomy just to do that, to make that, you know, replicable, reproducible, and to foster collaboration. So yeah, unfortunately, no, our simulations aren't available right now, I'm afraid.
Thanks.
All right, I have another question, and it's about sort of the same study, the one with the multiple agents and the impact on their communications to the search algorithm and the meta reasoning around that. My question is with regard to the modeling of the communication dropouts, and I'm curious because agents who are doing a search or mapping kind of thing often try to occupy the same place in space to achieve their goals, but presumably the communications, I mean, I was wondering if the communication dropout modeling was like based on distance between the nodes at all, if it was like sort of realistic in that sense, or if it was more randomly done, and if that has an impact on the kind of meta reasoning effect.
Thanks. That's a great point. We, in our team, Michael Odie, who's a faculty in aerospace engineering, was our communication expert. He's done work on that for years. And in our studies, we looked at different models of communication dropout. We used, you know, simple random models, such as a Bernoulli model, right? Basically a coin flip. We had another type of Markov process. But then we also looked at the Rayleigh fading model, where distance is a factor in the probability of the message being lost, as well as other factors. So we did look at a variety of things, and I believe the results I showed you today are from the Rayleigh fading model that we used. We had to, you know, this was in simulation, so we built a computer with multiple processors to represent, that could run the different agents, and then we had to simulate the communication process with this random, you know, dropout phenomenon.
Thank you. We do have time for one more question. Anyone else? I think that's it, Dr. Herrmann. Thank you so much. It's a great presentation. And that's it, guys.
Okay, well, thank you again, and please feel free to follow up with me if you want additional questions or information. I'll do my best to get that for you. And again, I hope everyone there has a great weekend.